Finite and Infinite Sets, as per the syllabus of 5th semester BSc Mathematics, Real Analysis. When we say a set is finite or infinite, if counting of elements exhausts, we say a set is finite. If counting doesn't terminate, we say set is infinite. This is the layman's definition. Now we are going to define very precisely using mathematical concepts. Firstly, define what is an empty set. We know an empty set is a set which has no elements. That means 0 elements. When we say a set has n elements, a set has n elements for some n in n. If there exists a bijection f from n, that is set 1 to etc. n, a set of first n natural numbers, onto the set S. So if there exists a bijection from Nn onto S, we say that set S has n elements. A set is finite if it is either empty or it has n elements for some n in n. A set is infinite if it is not finite. Now some properties. A set has n elements if and only there exists a bijection from S onto set 1 to etc. n. If you take any set S, we say S has n elements if there exists a bijection from set 1 to etc. n. Similarly, suppose we have a set S which is in bijective with set 1 to etc. n, then we can say S has n elements. Two sets S1 and S2 have n elements if and only if there exists a bijection from S1 onto S2. A set T1 is finite if and only if there exists a bijection from T1 onto another set T2 that has n elements. Suppose there exists a bijection from a set T1 which is unknown to us, suppose, onto another set T2 that has n elements, then we can say T1 has also n elements. That is, T1 is finite, and the converse is also true. Uniqueness theorem. If S is a finite set, then the number of elements in S is a unique number in D. Proof. Let the number of elements be not unique. That is, there exists some m and natural numbers not equal, suppose, such that there exists bijection from S to Nn and S to Nm. If we assume S has n elements, then there exists a bijection from Nn to S. If we assume that S has m elements, there exists a bijection H from Nm to S. Now from this figure, by the idea of composition, we can see that there exists a bijection F from Nn to Nm. That is set 1 to etc. n and set 1 to etc. m are in 1-1 correspondence. We know that is possible only if m equal to n. So what we assume is a contradiction. Hence, if S is a finite set, then the number of elements in S is a unique number in n. The idea of the proof is to observe that the set Q plus means set of all positive rational numbers is a denumerable set first. In all the set To prove set of all rational numbers is denumerable, we will prove first the set of all positive rational numbers is denumerable. Set of all positive rational numbers means you can list as a in the rectangular arrangement like denominator, rationals with the denominator 1, then rational with the denominator 2 like that. You see here 1 by 1, 2 by 1, 3 by 1, 4 by 1, etc. 1 by 2, 2 by 2, 3 by 2, 4 by 2, etc. This way you arrange. All the rationals, positive rationals you can list in the rectangular form like this. Having denominator 1 in the first row, having denominator 2 in the second row, like that you arrange. After that, you rearrange the elements by taking elements diagonally. First row 1 by 1 you write. So taking the elements diagonally, as in the picture, you rearrange the rationals as 1 by 1 in the first row, 1 by 2, 2 by 1 in the second row, 1 by 3, 2 by 2, 3 by 1 in the third row. Likewise, you can see that any p by q rational is actually in the p plus q minus 1th row as pth element. See, 3 by 2 is here, 3 by 2, 3 plus 2 minus 1, that is 4th row, third element, like that. So this way we can say that q plus is the set of all positive rationals is a sequence, hence it is a denumerable set. Similarly, q minus, the set of all negative rationals is denumerable, and the set of all rationals is a union of set of all positive q plus, q minus and set 0, and hence it is denumerable. Now, another method, another way we can also establish that q plus is denumerable. How? That we have taken q plus set of all positive rationals. We know n cross n is a denumerable set. N is a denumerable set. So there exists a bijection from n to n cross n. From n to n cross n, there exists a bijection. Now you define G from n cross n to q plus. You know, any n cross n is m by n, m comma n. Any rational number, positive rationals is m by n form, where m and n are natural numbers. So any mn is taken to m by n under this function G. And you can see that 1, 2 is taken to 1 by 2 and 2, 4 is also taken to 1 by 2. 2 by 4 is the same as 1 by 2. So it is not a bijective map, but it is a surjection. It is a surjection. For any q plus here, you can find a mn here. And for any mn here, m by n you can find a mn here. Therefore, G is a surjection from n cross n to q plus. F is a bijection, hence it is a surjection. So F is a surjection from n to n cross n. G is also a surjection from n cross n to q plus. Now you take G composition F, and that is a surjection from n on to q plus. So by the definition, clearly q plus is actually a countable set. Now we have to prove countable union of countable sets is countable. That is, if AM is countable, then union AM is also countable. Now to prove A means the collection of union of all AMs. That is union of all AMs here. We have to prove there is a surjection from N to A. That is, if you take any A here, correspondingly you should find an N here such that some surjection, if it is some phi of N is equal to that A. You have to prove. Now let A in union of A. Then there exists some M, such that this A is in A, because we have taken A in union of AM. Therefore, A is an AM for some M. Now, AM is countable. AM is countable. Therefore, there exists a surjection phi m from n to a. Phi m. There exists a surjection from phi m from n to a. Phi n now, there exists a phi m surjection phi m from n to m means for this a corresponding we are getting an n such that phi m of n is equal to a. Phi m of n is equal to as in the picture. Now define psi from n cross n to this a by psi of mn. We have a m here and an n also here. So psi of mn is equal to this a. That is phi m of n. Define psi from n cross n to m by psi of mn is equal to phi m of n as in the picture. Mn is mapped to this a and this a is nothing but phi m of n. Then there exists a function from n to n cross n by f of n is equal to this mn. Now imagine psi composition f. Psi composition. Clearly it is a surjection from n to a. N to a. N to a. Hence, union am is countable. Now another way, also we can establish this result because am is countable. Am can be listed as a sequence like this. A1 can be listed as A11, A12, A13, etc. A2 you can write as A21, A22, A23, etc. Likewise you can. Now taking elements diagonally, A11 you write in the first row, A21, A12 in the second row, A31, A22, A13 in the third row. Like that, as we discussed in the case of set of all rationals, positive rationals is countable and enumerable. Here also we can list all the elements of union AM in another rectangular form, like in the first row A11, second row A21, A12, A3. Any AMN is in the mth element of m plus n minus 1 row. Hence, union AM is a countable set. Then the last theorem in this section is Cantor's theorem. Cantor's theorem says that if A is any set, then there is no surjection of A onto the set PA of all subsets of A. You cannot define a surjection from a set to its power set. This is A. Suppose A has, we are illustrating with an example like this. A has X, Y, Z elements and PA no. A is a subset of A, therefore A is an element of PA. And other elements of PA are set X, set Y, set Z, set X, Y, set Y, set Z, X, Z like this. If you define a map from a function f from A to P of A, of course, for each element x, y, z, there should be some images here. Then only f becomes a function. So f of x, let us take set x. Fy is equal to set y. Fz is equal to set z. Clearly, the function is defined, but there are elements remaining here which are not having any connection with elements of A. So, this f cannot be a surjection from A onto P of A. Now we are going to prove an analytic proof for this. This is our situation. A is a set, given set, and PA is its power set. The elements of PA are A is there, and all the subsets of proper subsets of A, including empty sets, are here. Now we want to prove there is no surjection from A to P. Suppose there exists a surjection F from A to P, A on to PA. That means any elements in PA if you take, correspondingly there is an element in PA such that F that maps to element to that power, element of a P of A, that is subset of A. That means for any B, if you take in P of A, I have taken a B here, an element of PA which is a subset of A. And B is a subset of A. Here also, the same B is here also. B is a subset of A. So to this B, corresponding to this B, there exists a B such that FB is equal to that B, of course, because FB is assumed surjective. Now this B is an element of A and capital B is a subset of A. Therefore, B may be an element of capital B or may not be an element of B. So for any A if you take here, that A may be in f of A or may not be in f of A. Suppose you take A in f of A. There are two possibilities here. If you take any A and its image f of A, if you consider it's a subset of A, there is an element of PA, this A may be in f of A or may not be in f of A. Now you consider a set D. A set D consisting of all A in A such that A is not in f of A. This is D. This is D. And D is of course here. And what is the peculiarity of this D? D is all A in A such that A is not in f of A. This element is not in this f of A naught. Here A naught is such that A naught is not in f of that way. So consider the set D such that the set A in A for which A is not in f of A. Its element, we are taking f, all A here. All such A we are taking such that this A is not in f of A. Whenever A is not in f of A, that element we will take in D. So this way we form a subset D of A. Clearly D is a subset of A. Now since f is a surjective function and D is a subset of A, corresponding to this D there must be an element A naught here such that this f of A naught is equal to D. Now there are two possibilities like this. A naught may be in D, A naught may not be in D. We have taken D, a subset of f of A, by the definition such that all in A for which A is not in f of A. Now this A naught may be in this D or may not be in D. Now let us take the case A naught in D. If A naught is in D, what is the meaning of that? What is D, the definition of D? All A in A for which A not in f of A. So if A naught is in D means A naught is not in f of A naught. F of A naught is D. That means A naught is not in D. So you are getting A naught in D implies A naught is not in D. It is a contradiction. Now assume the other case. Suppose A naught is not in D. If A naught is not in D, that means A naught is in f of A naught. That is A naught is in D. Again you are getting a contradiction. If A naught is not in D, A naught is in D. So it is not possible to define a surjection f from A onto P of A. That's the proof. Now there are some problems given here.